Now we know the form of Pausa double integral. So Pausa integral is a way to calculate the drain current, and in order to calculate the drain current, actually we have to perform something like this, starting from our coordinate, channel directional coordinate from 0 to y, and our position wise current density or current should be integrated. This is the basic form of our current calculation. Of course, this one can be a function of position in general, but due to the electron continuity, if you remember correctly, it is written in form of this simple equation. So in order to satisfy this electron continuity equation at steady state, of course we must have a vanishing time derivative. Simply speaking, now this Jn should be a constant along any y directional position. So here we have position wise y directional current component, and if we make some resolution according to this vertical direction, then now we can think about the electron density function of x, so at given y position. And generally we have a certain trend of exponentially decaying behavior of our electron density. Electrons are showing its peak value nearby this x equal to 0 silicon and silicon dioxide interface, and it is rapidly diminishing. So in order to calculate this current, so which is written in ampere unit instead of ampere per square centimeter, so this is current density, but we must take the area integration of this current density to eventually get this terminal quantity. So in this case, what is this area component? This area component can be decomposed into two parts. So the A now can be expressed as so in its magnitude. So in this case, now we can say that there is a x directional derivative, and also we have a g direction, but that is just w. This is width of our transistor, and along the width direction we assume the homogeneity, so it is just okay. Now this aerial integration just converted into x directional integration, so that's the reason why eventually we have some quantities like 0 to L for dy, and also x directional one, 0 to some deep inside into our substrate or end of our inversion charge, inversion layer, and also we have something like this Jn, sorry, so Jn it's a y directional component function of x and y. After that, the all other parts are just mathematical conversion. So dx is converted into the phi s, the phi, and also we convert dy to dv. So that was all for our transformation, coordinate transformation to get the Pausa equation. Finally, we have to have consider electron density at a certain position, but it was possible because now we know the exact form of our electron density. That was the Pausa equation. So today we start from how can you actually apply this Pausa integral, double integral, seemingly quite complicated, to the realistic problem. So before starting today's talk, so let me just remind you the form of our Pausa equation. So once again, here you can see this is Pausa double integral. As you can see, drain is shown here, and this 1 over L factor comes from this dy integral, and W is coming from our dA component, and all other terms Q, mu, that is corresponding to the Jn component, and this is nothing but just integrating our electron density related quantity. This is more related to the electron density, and this is E dx. This is d phi over d x, and this is obtained from the x originally x directional component. So that was Pausa integral. Maybe you remember that if we really wanted to evaluate all of these complicated integral, then we have to find out which are unknown variables. So Q, universal; mu, that is model parameter we assume; W and L, they are design parameters. You can draw your transistor's width, and you can draw your transistor's length, so it's okay. And VDS, this is the bias voltage you have applied to your drain, so this is your decision. And what else? This is delta. This is not exactly known, but this is quite close to 0, so it doesn't matter. And you know the form of E sub x and Ni, intrinsic carrier density. Also, you know this value at 300 Kelvin. It's about 10 to the 10 per cubic centimeter. How about Na? This is doping density, and you know the substrate doping density of your transistor. This is summer voltage, and this is just they are just integral variables. So if we just review this quite a complicated expression, the only thing we have to find out is actually this surface potential phi s at given position. So at given v value, so this is corresponding to given y value, what is the value of our surface potential? That is the main topic of our actual application. So you can see that how can we determine phi sub as a surface potential? But fortunately, quite fortunately, we know the exact expression for our surface potential for a MOS capacitor. Of course, we know that this is exact only for a capacitor, not for transistor, which have x directional and y directional. But how can we apply this expression to our transistor case? There was a magical word we have introduced in the previous lecture. That was gradual channel approximation. If we adopt this gradual channel approximation, although our system is two-dimensional, but as much as Poisson equation is involved, we just convert it to or reduce it to one-dimensional problem. So we can use this expression without only minor modification. What is the minor modification? The minor modification comes from this minus v term. So when you consider just MOS case, you assume that quadriform potential for electron is 0 all over your device. But now in this case, you have to introduce position wise. This is really position channel wise quantity you have to assume. But except for this small difference, and even in this case, we can say there is a certain given number, 0.1, 0.2. Think about this one. Now, here we have a transistor, and please name them. Here, 0 and y equal to L, and say that V equal to 0 and V equal to, for example, VDD. If I say in this way, then my question is, if we select one point at this transistor happen to be, for example, just half of L, then what will be the value of your V at this Y equal to half L point? Actually, we have no idea about the exact value of this V value at a given position. Actually, that is the one we wanted to calculate. But one thing we can say certainly is this is within the range of 0 to VDD, because this is just a smooth and ever growing function, ever increasing function. So simply speaking, if you change this value, for example 0.1, then this upper bound it will be just 0.1. If you say I will increase the bias voltage to 0.2, then this upper voltage will be changed to 0.2. So you can treat this V value as an equivalent of your coordinate value Y, channel directional coordinate Y. There is one-to-one correspondence between V and your coordinate Y, and their variation, this variation is over 0 to L, and its variation from 0 to VDS. That is quite simple, and within this value, of course, within this voltage range, you can find many intermediate values, and for each intermediate value, you can calculate phi s. So if I summarize this situation, then even we can think about a simple table. So Y starting from 0 to L, and V, and it is starting from 0 to VDS, and later we can think about surface potential and start from surface potential for source side and surface potential for drain side. We can think about this table, and what we try to know is these are given, Y values are given. However, what is the relation between these two quantities? So that is not known to us, so we have to find out. But fortunately, with this equation, so assuming a value of quasi-Fermi potential, then you can calculate the surface potential. So in this table, the relation between these two quantities, V and phi s, can be solved by this equation obtained from MOS capacitor. So that is quite straightforward. If you can ask me, is it really easy to calculate the relation between V and phi s? Then I have to say that this is almost trivial, but it is not zero. So at least we have to spend a few computation to calculate this quantity. So let me give a simple example. So say that gate voltage is given as VGS and drain voltage is given as VDS, and please try to calculate your drain current. Then how can we do this job? Then starting from our power psi integral, so we can for example, here we have originally the integration over our voltage or electron quasi-Fermi potential V, but that is now converted into what? Converted into just integration. So you can easily think about this one. dV starting from 0 to VDS, that is changed to this way, the delta Vj, and I say that starting from certain j value to some value, for example 100, then isn't that it's okay. So by performing this integration, you will have just VDS, and by integrating this this summation, also you will have VDS. So are you with me? In this case, I just integrate just number 1, but instead of this number 1, why don't you just introduce this f? Then we can think about this f, and which is evaluated at certain interval at v sub j. So here j is used to the index for our slots. Then we can have quite good approximation, numerical approximation for this integration. So I have done just a simple change from the exact integral to some approximate summation, but I think that everybody in this room can accept this approximation. Of course, if we introduce this upper bound, upper index to, for example, 1000 instead of 100, then what will happen to this delta Vj? Then we will have almost 10 times smaller delta Vj. So you know, delta Vj is approximately just VDS divided by 1000 or 100. So our entire integration domain is divided by the total number of bins or slabs in this case. So then you can have approximately many rectangles, and the width of your rectangle is given by this simple rule. So VDS minus 1000 or 100. Why I'm saying that approximately? So in my own calculation, when j equal to 0 and j equal to 100, I introduced just half of it. But you know, this is just okay, because you can do this summation quite accurately by applying large number of bins or slabs in your calculation. So are you with me? So I'm saying that in this stage, I'm saying that Pausa integral is really double integral, but one of those integrals can be converted into just a simple summation. So this is a Riemannian sum approximation. Of course, in order to have the real equality, but in that case we have to increase this number of bins to the infinity. If we introduce so many bins, then actually our summation will approach it to the exact integral result, but we do not pursue that kind of accuracy. So we just say that approximately this is good enough to have 100 1000 bins for our calculation. Are you with me? So then now I will just use a certain value, but this value is really depends on your choice. So why that has specific value? This value is not that much specific. So if you have, I want to increase my transistor width 10 times. If you have 10 times wider device, then you can use just 10 to the minus 16, 10 times a higher value. If you say I will use just 10 times narrower device, then you can just say that 10 to the minus 18. So this value itself is not a special value. So just to use on your own value. But so in this case, Q, this is really a universal constant, and mobility, of course, this is not a universal constant. Depending on your transistor, you may have different values, but one thing is you cannot assume too high value or too low value for your effective mobility. For example, if you assume that why don't we have 10,000 square centimeter per volt second, then obviously this is wrong. You cannot assume this value. Or why don't you just say 1 square centimeter per volt second? Oh, this is really achievable, but this is way too high to be really used for your transistor. My suggestion is maybe when you really use your transistor, your value for mobility will be around about just a few hundred or several 10 terms of square centimeter per volt second. This is your value. Please do not overemphasize or overrate or do not use too low value for your mobility. Actually, for engineers, this small difference really makes a big difference. For example, 100 and 200 to you. So, like the ones in studying this subject seems to be just okay, because this is a matter of choice. I can just I will use 200 instead of 100. Wow, I have twice more current. But in reality, in our mass production, having just 1% or 2% higher values for our mobility, that really makes a big difference. So in real device, mobility value is critically important and really difficult to be improved. But anyway, you have to remember the reasonable range of your transistor mobility. So certainly that should be 100, not 7, 5, 900. This is just the orders of 100, 200, 300. These are values you will see in your practice, and also around certain 10 square centimeter per volt second. That will be your value, and you will try to improve. If you are assigned to those parts, then you will devote your entire effort to improve the mobility values, just a few percent. Okay, so what was? I will use this value, so there is no specific value we will use. Then you can ask me this question. Okay, I understand. Then what is, in this case, what is exact value of W and what is the exact value of L? In order to calculate this value, my assumption was, well, mobility is about 300 and W over L equal to 1. If I use this value, then I can get this specific value. Then when I say W over L equal to 1, then what is the real meaning of this calculation? Is my L equal to 10 nanometer and W equal to 10 nanometer. That gives us W over L equal to 1. 1 micrometer, 1 micrometer. That will give us once again number 1. 10, 10. Also that will give us also once again the W over L equal to 1. So then what is the exact value used for this W over L ratio? Please note that we are currently talking about the long channel limit of our transistor. So in this long channel device, actual value of L and W does not play any role in its IV characteristics. Only W over L is important. So simply speaking, if you have a 10 micro by 10 micro device, then its IV characteristics, when all other parts are the same, then that will be equal to that of 1 micro by 1 micro case. So there is a scalability. 10, 10, this is huge. And if you reduce it by factor of 100 times, reducing the length 10 times and width by 10 times, then your transistor will conduct exactly same amount of current at a given bias condition. That is the assumption or the theory for long channel MOSFET. This is really difficult to believe, but that's true for long channel limit. But in reality, nowadays we are not no longer using these long channel devices. So therefore, transistors current is heavily depends on W and L, not only on their ratio, but the result is individually dependent on W and individually dependent on L. So please note that this is just a long channel limit case. Okay, so now then if I give you this semi-discretized form, then can you calculate it by your computer program? Summation, it is good, and this is just a number, and the only remaining thing is evaluation of this internal integrand. Then how can you perform this integral once again? In this integrand, still we have integration over electrostatic potential phi. So therefore, we must perform this phi wise integral once again. Once again, this is just a given number and summer voltage, and here we have an important one, V sub j. This is the J's slabs or J's bins electron quadriforming potential. Then how can we know this value before performing this integration? But fortunately, this is just outer integral, so we can assume that there is a given value of V sub j. So you may assume that this is a given number, 0, 0.1, 0.2. Yes, for each value you can perform this integration. Then if this is given, then electric field itself is also can be calculated by our expression. Then the only remaining thing is here the upper bound of our integral. Here you can see, here we have a upper bound of our integral, and this is just phi sub s. So simple rule is when you have V sub j, please calculate your phi s. Once, how can you calculate phi s? By solving this equation. By solving this equation, you get the surface potential, and with that surface potential, just to perform this integration. Of course, for that purpose, you must also change it to delta phi whatever. So also you have to convert it to summation, from integration to summation, but I think that you can understand its limit and numerical error. Okay, so then okay, here you can see that the phi wise integral can be once again converted into just a summation with a very small one. So in this example, for example, I have introduced 0.1 millivolt as just the size of my bins. So you can do whatever you want to have. So now let's try to, this slide just shows that how can you calculate this phi s. So let's assume that you can do it by some way. After that, this is the result of our calculation. So please have a look at this one. Here, x-axis or horizontal axis is corresponding to electron quadriform potential. This is V. And This is what is this? This is integrand of voltage integral. So now you can see that by integrating this one, then you will eventually have the current. By integration, you can calculate a certain value. So please, my suggestion is, I understand that all of you are not quite good at writing a code. Some of you feel this is not my job, but my suggestion is, you don't have to be a real expert on doing all kinds of this numerical job. But in this slide, I just sketched how can you do it by a step-by-step way. So please at least try to follow my suggestion. Then you will feel that the hands-on experience on how can we use the Pausa integral. Actually, looking at the result and looking the beautiful graphs, and that's the way we do. It is really easy to follow, but writing the code by yourself, that is a completely a different story. So please, my suggestion is do it by yourself. So this is just a sketch for that one. So by using this kind of integration, double integration, then we can get ID values at a given VGS and VDS. So this curve, this IV curve simply means that one dot shown here is calculated by performing that double integral for given VGS and VDS value. So the graph shown here means that I have done it so many times with different pairs. So different values of gate voltage and drain voltage. I just calculate it and plot them all. This is typically called as output current, output characteristics, and here horizontal axis is corresponding to VDS, and vertical axis is corresponding to, of course, ID. And here we have many different branches. These branches are corresponding to different values of VGS. For example, if I remember correctly, then this is obtained from 1.1, happen to be our VDD value, and I just down the gate voltage by amount of 0.1 volt. So simply this is corresponding to 1.0, 0.9, 0.8, 0.7, 6, 5, 0.4. For example, if we apply 0.4 to our gate terminal, then the amount of current is really much lower than the on current. Where can you find this on current in your output characteristic? Please pick up the point. Where can you find the on current? This is the point for your on current. Why? On current is obtained when you apply VDD to both of your gate terminal and drain terminal. This is your drain terminal, and here you have VDD. And there are many curves, and among them, this topmost curve is corresponding to the case of VGS equal to VDD. So this point is your on current, and compared with this on current, when you apply 0.4, the current is really much lower than the on current. This is I on. And when, for example, if you apply 0.3, then of course you will see almost horizontal line touches to I equal to 0. So maybe your threshold voltage is around 0.3 volt. Maybe you can have. So this example simply means that although seems to be a little complicated, but anyway, by using this Pausa double integral, we can predict this IV characteristics of this long channel device at arbitrary bias condition. So it doesn't matter where we have a sufficiently high gate voltage or sufficiently low gate voltage. Although I'm not shown it here, for example, it can also calculate the value of your drain current at VGS equal to 0.0 volt without any difficulty, and you have a very smooth and beautiful curves for your IV characteristics. How did you get this information? Please remember your all lecture progress. You start from this two-dimensional cross-section, and by applying certain reasonably good approximations, among them the most important one is gradual channel approximation, and after that by integrating your current density quite rigorously without introducing much additional approximations, you were able to get this information. Of course, the cost is for every V value you have to calculate your surface potential, and this pair really numerically calculated by solving this equation. That is the only computational burden we have to pay for our Pausa integral. Nowadays, everybody with a very small computer can do it quite quickly within 1 second. So there is no doubt about it. But please note that when this paper was first published, it was 60 years ago. 60 years ago, calculation of this equation for every available V value, that really requires a quite good computer. So people thought that, okay, that theory looks beautiful, and if we are quite heroic, and if we try to calculate that information only once, we can do it. But every day, can you do it to them? Actually, that was too much. So it was quite beautiful, but has not used for long time. Okay. So finally, my discussion about Pausa integration ends with the comparison with the more rigorous one. What is the meaning of more rigorous one? We have already done it quite reasonably. Yes, Pausa is really rigorous, and we have done our best to get rigorous result. But please note that from its starting point, we have already assumed gradual channel approximation. That was one thing. So is it really 1% difference, 2% difference? What is the exact value? So let me just show it to you. So for that purpose, we can just entirely analyze this original two-dimensional space. Then the result is shown here. These dots are Pausa, and here we have a solid line corresponding to the numerical calculation of this entire system. And unexpectedly and a little bit disappointingly, so you can see that here difference comes. Why do we have this difference? Maybe you can ask me this question. Then Pausa is it not accurate enough? The reason we have this difference comes from the structure we have assumed. In this case, I have assumed that L equal to 1 micrometer, and also W equal to 1 micrometer. So if we evaluate W over L factor, then that is just number 1. But in reality, here you can see that the position, here position means that y coordinate, and here you have y equal to 0 in our situation, and here you can see y equal to L in our situation. It is not exactly 0. 0 is shown here, but in my numerical calculation, I have to also consider source and drain, n plus source and n plus drain. So coordinate is a little shifted, please understand. So simply speaking, in real device, this is the region assigned to our channel, and you can see that what we have assumed in our model evaluation, Pausa integral, we assume that everything is just homogeneous till the end of y equal to L. So therefore, we assume that this full length, full 1 micrometer assigned to our channel region, but in reality, even in this relatively long channel device, 1 micrometer device, still we have a certain change of potentials according to highly doped N plus region, and this is almost intrinsic or p-type substrate. Here we have N plus plus, and here we have a p-type substrate. So therefore, you know, at the beginning of our lecture course, we first talk about the bi-length. When doping is rapidly changing, abruptly changing, we need a certain amount of length scale to compensate that effect that was measured as the bi-length, and we need certain length scale corresponding to that one. So therefore, this part and this part cannot be fully used as our entire MOSFET channel. Small part of these two parts should be considered as a non-channel part of our unused part of our transistor. So simply speaking, our actual channel in our numerical calculation should be considered as around here and around here. So your actual L value is a little bit shorter than your drawn length when 1 micrometer. That's the reason why when we draw the W over L, when you evaluate this one, actual value used for this L should be not exactly 1 micrometer, but net length. So that's the reason why now here we have a slight increase of our current. So simply speaking, although we have drawn our gate as 1 micrometer long, but internally this transistor has a little bit shorter channel. So L is slightly shorter than 1 micrometer. So that is increasing our drain current observed in this case. Of course, instead of this example, 1 micro example, if I go to 10 micro by 10 micro example, then what will happen? If I go to 10 micro by 10 micro example, this dead zone will be the same. So although length is 10 times longer, but dead zone length is the same, so this effect can be much more diminished. So we expect that instead of this 1 micro by 1 micro, if we switch it to 10 micro by 10 micro, real long channel limit, then we will have a much closer result for our TCAD simulation, so numerical calculation. So please note that already we feel this one. To all of us, 1 micrometer seems to be quite long. Oh, that is almost infinitely long. But even in that case, we have to consider non-ideal effect. In order to support this channel, MOSFET channel, then having only MOSFET channel does not provide us a MOSFET. We have to introduce a source and drain unavoidably. Then these source and drain makes some an non-ideal effect into our channel. So therefore, already we can observe the deviation from ideal behavior of MOS characteristics. So of course, this topic will be the main topic of our remaining lecture, remaining semester. So I have already told you that we have 3 topics in our entire semester. First one was understanding MOS capacitor. You have done it, and now we are covering the long channel device, and we are working on this one very actively. And after this midterm examination is over, then we will move to the short channel devices, the real device we have to deal with. Then in that case, we will see a lot. We will discuss a lot about how can you deal with this non-ideality. Okay, so do you have any question? So that was the first part of our today's lecture, and I hope that everybody now understand there is a well-established way to calculate the IV characteristics of a long channel device. Although that is quite cumbersome, but at least we can do it. If you understand that one, then I think that this is quite successful. And now let's go to more practical way to calculate this IV characteristics once again. So I have to give you the motivation. Then you can ask me this question. Well, if power integration is so good, then why we have to calculate this additional technique to calculate IV? Is it, for example, this new technique called as a charge sheet model, is it as accurate as a power integral? The answer is unfortunately no. This model is known to that it generates error of current almost close to 10% error. In its worst case, it can generate about 10% difference in its IV characteristics. Then you can say that, well, 10% difference is not acceptable to the engineers. Engineers are really concerned about a few percent difference. Then why do you ask me to develop a new model with 10% maximum error? The motivation is, once again, this is really calculation of a power psi double integral is too computationally intensive. It is really true that already 60 years ago, calculation of power psi that takes forever. So after about I think that more than 10 years later from the publishing this power psi double integral, so then now charge sheet model is published, and that is the basic model most of our transistor models are currently using. So simply speaking, it is not used for because it is most accurate. It is used because it provides us reasonably fast calculation and reasonably good calculation result. So we are compromising between accuracy and speed. So for example, if we have speed and accuracy, then what is the best point we wanted to pursue? Best speed, the fastest one, and also most accurate one. So this is the heaven of engineers. We wanted to arrive at that point, but unfortunately in our current discussion, so where can you find the power psi? Power psi is located here. It is quite accurate, but its speed is awful. So therefore, instead of this one, we wanted to move in this direction. The best way would be just parallel shift. So keeping the accuracy and just increase the speed. Wow, but that is not usually achievable. So what we have done is slightly reasonably sacrificing our accuracy, but instead of that increasing efficiency quite a lot. So that is our current model, will be called as a charge sheet model. Then who decide this degradation is acceptable or not? For example, 10% error, is it acceptable or not? Who decided that one? I cannot give you the general rule for determining which model is acceptable or not, but you know that. So there are many users of those models, and when they feel that okay, I can live with these models and I can design my circuit with these models, then that is acceptable. But if somebody say that oh, no, this is too inaccurate to be actually used in our circuit design, then that model will be discarded. So there is one single rule and determine everything, but it takes some time to really determine which one can survive and which one should be discarded. Okay, so the main motivation is shown here. In order to calculate the charge, then we had to integrate in this way. This is nothing but here we have d phi, and this was obtained as d phi over dx. So by combining these two components, so we just recover our dx. Simply speaking, in order to calculate our electron density, what we have done is just to really vertically integrating our electron density. We have done it by performing this integration. That was our quite exact and quite accurate approach. Here, the idea is quite interesting. So instead of calculating these all kinds of numerical integration, so what this guy says that invariant charge is simply given as the difference between the total charge and depletion charge. So we can calculate this QS charge exactly when we have phi s. Do you remember? So why don't you just come back to our previous lecture material? I'm not quite sure where can you find it, but let me just guess. Okay. Oh, why don't you just go to 5. Oh, here you can see that we have already studied that when we have certain surface potential, then we can immediately calculate the total charge without performing any integration. Do we need integration all over this vertical structure? That was not necessary because we have done this integration already by our hands. So that is already done. So we don't have to perform numerical integration here. Simply speaking, in this expression here, Qi, we need x, y's integration in this approach. But in this new approach, Qs can be calculated without xy's integration. There is only one single expression to calculate for Q sub S. You can immediately calculate this one. And if we have good enough approximation for Q sub D, depletion charge, let's say that, I'm not saying that this is exact, but if this is good enough, then we can say that our calculation for Q sub I will be also good enough. So think that A and B, their sum is known to be exactly 100. Then what is B? Nobody knows actually. But let's say that if A is known to be about 70 within, although 70 is not exact value, but it just slightly changed from 0.1, 0.2, then we can certainly say that although this is not exact, B is about 30. Quite similarly, in this case, what is the exact quantity? Q sub S, this one is really exact. And if we introduce good enough approximation for Q sub D, then now we can say we have a good enough approximation for Q sub D. That is the point we sacrifice our accuracy. Previously, our QI was really accurately calculated by performing this x-directional integration numerically. So there is no other approximation. But now here our Q sub I is approximately obtained. Then what is the gain of this approach? Sacrificing the accuracy, but instead of that, there is no integration, and this one is also no integration, so we can kick out our integration once. Pausa dictates us double integral, but by introducing this approximation, we already kick out the very first internal integration. So it means that now we have only single integral over our length scale, y scale, or dv scale. So that is one thing. Are you with me about the motivation of this charge sheet model? Then how can we calculate this Q sub I? Or in this case, most important one is it good enough to approximate this Q sub D? How can we determine depletion charge? For that purpose, we introduce well-known depletion charge approximation. So we assume that here we have a certain depletion width, and the entire NA is depleted up to WD. So simply speaking, x equal to 0, and we say that up to x equal to WD, our entire channel region is depleted. So now we have minus QNA, net charge density, shown here. So by applying the expression for Q sub D, you can have this expression. It is a function of surface potential. Within depletion approximation, this is true, and within depletion approximation, now we can have this one. Yes, so I think that this is really good enough to calculate Q sub S, and this is corresponding to minus Q sub D. So now we can have really simple expressions for Q sub I. Please revisit this equation. Do you know COX? Yes, we know. This is a known quantity. Do you know VGS? Yes, this is also given quantity. Flat band voltage. this is also given quantity. Epsilon, Q, Na, all of them are already known. So in this case, we can express Q sub I only a function of surface potential. Once we know the surface potential, then we can calculate Q sub I. So, but please note that this is an approximate one. Once again, this is approximate one. But well, this one gives us the comparison between 파오사 and charge sheet model. The charge sheet model is the name of the approximation we have already seen here. In this case, here electron quasi-forming potential, this is corresponding to the V value, which is corresponding to Y value, and integrated electron density means that this is corresponding to Q sub I. And blue and red are obtained from Pausa and charge sheet model. Can you recognize the difference? Here, although we have a small difference, the difference is really small. So now you can see that in this case about 1% error is occurring in this Pausa integral. Then you can ask me this question: why we have such a good result? Oh, too good to be real, but it is because you know that this expression, the expression for our Q sub S, this one is really exact one. QS should be given as this expression. This is really exact, and the accuracy of this approximation really depends on the quality of our depletion approximation. When depletion approximation gives us a reasonably good result, then that is quite reasonable. And this one just shows that in our case, this is really good for our practical case. Of course, I'm not saying that this charge model is really good enough and we can use it for everywhere without any further quality degradation. It really depends on our bias condition. So depending on gate voltages, sometimes it shows us better result or worse result, and usually in many cases it is known that near the threshold voltage we have the maximum error of this charge sheet model. But anyway, this is when we consider the simplification obtained from this charge sheet model, the accuracy looks just amazing. So up to this point, maybe you feel that, oh, that sounds great. Then now let's just numerically perform the remaining y-directional or v-wise integral, the outer integral. However, the beauty of this approach is, once again, even this second integral, the outer integral, means that dv integral, that can be also eliminated by this model. So simply speaking, after when we finish this model development, there is no integral at all. Although we had double integral, two integrals, but by introducing this new model, changing qi as a function of phi s, not instead of v, this one, then now we can get quite a simplified result. So then let's have a look at this one. This is the expression we have to calculate originally. So if you remember correctly, so in our Pausa integral, here we introduce a quite a complicated integral to evaluate this q sub I. Where can you find it? This is the model we have used to express our q sub I. But now we have a much simplified expression for q sub I, and it has very specific characteristics. So please try to find out V in your expression. Here, can you find V? Then please, once again, please come to this the more exact, the exact expression, and please try to find out the dependencies on surface potential and V. Where can you find this dependency on V? In this expression, you can clearly find the dependency on V, and also can see the dependency on surface potential. So in its original form, we have to consider q sub I as a function of a surface potential and quasi-Fermi potential. But in this simplified charge-ship model, what we can see is now q sub I is no longer a function of electron quasi-Fermi potential. We just have a dependency only on q sub phi sub s. So in that case, here we go. Instead of having this one, now q I v dv was our calculation, but now we say that this one is phi s. It's okay. We can just say with our charge sheet approximation. But integral variable is still dv. So why don't you just instead of this one, say d phi s and dv d phi s. I have not changed anything, just to convert it to as an integral with respect to phi sub s, and now we have additional factors coming from coordinate transformation. Then now we have this expression. And upper bound and lower bound, please think about it. Previously, our upper bound, lower bound was source voltage and drain voltage. But now we have to consider surface potential at source side and surface potential at drain side is required. This one is exactly showing that information. Surface potential at source side and surface potential at drain side is used as the lower and upper boundaries. Then after that, then everything is just equivalent. Then please remember, its form was amazingly simple. Q sub I, now so simple. It is just given as just a linear constant term, linear term, and square root term. You can integrate these three functions quite easily. And another one is, now we have of course seemingly quite complicated coordinate conversion factor, so we will discuss it in the next lecture. But it is found that actually practically it is not that difficult to include this one. So simply speaking, q sub I, this is easy, and this is not easy but can be made easier and taking the integration. So now the answer is this integration itself can be done analytically. So now there is no need for you to actually perform these double integrals. Then too good to be real. So then what is the remaining cost? Of course, there is a remaining cost. This is not free. You have to calculate phi sub s at drain side. You have to calculate phi sub s at source side. You have to do these two calculations. But the advantage is really huge. Previously, you had y equal to 0, v equal to 0. And you had y equal to L and v equal to v ds. Previously, you had to introduce so many internal values and calculate this MOS capacitor for every slabs and integrated these values. But now in this simplified form, the only thing you have to do is evaluate it at source end, evaluate it at drain end, and all other quantities or all other evaluation can be done in an analytic way. So these two values, numerically obtained these two values, are just put into your analytic expression. That is really amazing increase of numerical efficiency. Of course, with a slight degradation of accuracy, but I think that everybody really loves it because the advantage is so obvious. Okay, so we will continue this discussion in next lecture on Wednesday. Thank you.